Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Welcome to today's lecture. And our today's lecture is about sorting. We are going to start a new series of lectures in which we will study what sorting is. So you might have already studied what is sorting and what are different sorting algorithms in your lab class or in previous class. But here we will discuss their abstraction in detail. Sorting is a concept that is deeply embedded in a lot of things that we do in our daily life. So it's quite often that we like to arrange things or data in certain order, and it's very natural. Sometimes to improve the readability of that data. For example, whenever you put some currency notes in your purse, or whenever you are going to give some amount in the form of currency notes, you keep them in some order. You keep the bigger notes at the end, and for example, you have got 1,000 rupees note, so you will keep the 500 rupee note above that. So if it is in order, so it becomes better to visualize, and it improves the readability, and you can be able to search your required note, your required currency note more easier, in fact. So the extraction of information is quick. So this is an example which you are, I think all of you use in your daily life. So it is not just about the notes. For example, look at this OLX site or any site that can be used as an online marketplace. So if you search, for example, car in this website, so it gives you options about how to sort them. For example, here you can see there are 4 options: newly listed, more relevant, lowest price, highest price. And for example, if you are looking some place for rent, so there may be some more options like distance from you, or distance from your workplace, or distance from the center of the city. So there may be many criteria on which you can sort your data. So sorting is really helpful feature here, and there are so many places where we like to keep our data sorted. So be it the language dictionary, where we want to keep the words sorted so that searching a word in the dictionary is easier. So in fact, this is a real life phenomenon. If we want to define sorting formally, then sorting is arranging the elements in a list or collection in increasing or decreasing order of some property. So this is very vital here, of some property. I have not written increasing or decreasing order of values. So I will explain it. The list should be homogeneous. It means that all the elements in the list should be of the same type. It doesn't mean that list cannot an element cannot contain more than one properties. It can, but all of these memory chunks, you can say, or blocks, their structure should be same. Their structure should be homogeneous. To study sorting algorithms, most of the time we use a list of integers, as you have done earlier, and typically we sort the list in an increasing order of value. For example, if we have the following list 12, 21, 6, 8 and 5, then sorting in increasing order of values will mean rearranging the above values as this: 5, 6, 8, 12 and 21. But if you want to sort it in decreasing order, so it will result in the following permutation of the above list. In fact, every list have got some permutation, mean some arrangements. So in all of these possible arrangements, all of these possible permutations, there is one permutation that is either in increasing or decreasing order, and that is what you have to achieve. It is not just, I told you that it is not just the increasing or decreasing order of the value. It can be increasing or decreasing order of some property of that value. So let me explain it to you. For example, if we have the same list 12, 21, 6, 8 and 5, and I want to sort it not just by the magnitude of values. I want to sort it on any other property of data. Magnitude is just one property, like increasing number of factors. So first I have to see how many factors all these have. So 12 has 6 factors 1, 2, 3, 4, 6 and 12. 21 has just 4, 1, 3, 7, 21. 6 and 8 guys had also got 4 factors 1, 2, 3, 6 and 1, 2, 4, 8. 5 have got just 2 factors because it's a prime number. Now you see, if I'm going to sort these values not by their property of magnitude but by their property of number of factors. So, and in increasing order. So increasing number of factors. So whenever I am sorting something in an increasing order, so the lowest value comes first, and then the second value, and then at the end comes the value which is of the which is the most which is the biggest value. So here which value has just 2 factors, so it is 5. So 5 will come at first. Now you see 5 had just two factors, and I have included in the top of the list, or in the you can say first index. Now 21, 6 and 8, their magnitude may be different, but I am not concerned with their magnitude. I am concerned with their number of factors, and with respect to number of factors, these all have the same magnitude. By magnitude I mean the same number of factors. So 21, 6 and 8 all have 4 factors, so they can be placed next to 5. So 21 is bigger than 6, so I am not concerned with the magnitude. So it may happen that I place 21 before this 6 as it was in the original list, because magnitude wise they are different, but with respect to number of factors they are the same, so they have the same level. And at the end I will include 12, which has just which has 6 factors more than animal in the list. So you saw it is not just the order of the only one property, magnitude. It can be any property of data, and that you have already seen in the slide where I showed you the cars that can be sorted with respect to different properties. Now a sorted list is just the permutation, one of the all possible permutations of the original list. So when we sort a list, we just rearrange the elements, and that is all. Now this was a list of integers, so we may have a list of any data type. We may want to sort a list of strings or words in a you can say chronological lexicographical order, the order in which they occur in dictionary. For example, here we have 5 values: fork, knife, screen, mouse and key. So with respect to alphabetical order, I will place fork first, and then it will be knife, key and knife. So K is the same, N and E is E precedes. So key will be second, knife third, and then it will be mouse, and then it will be screen. So sorting is not just doing something on integers, it can be on any data type. So car was another data type, so we sorted cars with respect to their different properties. And we may have a list of very complex data type as well. So core may have different properties like price, relevancy, date of inclusion in the database, and list can be sorted on any of these properties. If you can include more properties, for example the color, or the horsepower of engine, so you can have many more properties. Sorted data is good not just for presentation as we seen earlier, or manual retrieval of some information, useful information, but even when we are using computational power of machines. Now how? See, sorted data is really helpful. How? I will explain it in later slides. If a list is sorted in computer's memory, if a list stored in computer memory is unsorted, then to search something in this list, you cannot apply binary search. You have to just run linear search. Why? Because binary search works only on sorted data. So in linear search, what happens? What is the worst case time complexity? Order of n. So we start with the first element of the list and keep scanning the whole list until we get the element that was desired. So in the worst case, like when the element will not be in the list, or it will be the last element in the list, for instance, we will compare it with all the elements in the list one by one from left to right, and then it may happen that we may find the value, or search is unsuccessful. So if there are n elements in the list, so we will have to make n comparison. In other way, we would say it takes order of n, or the big O of n time. But you might have heard about the terminology big data. Just think about the kind and amount of data modern day computers deal with. So what if n is very very large and we take n raised to the 2 raised to the power 128 values? So this is a huge number, huh? And we want to sort this value. We want to search in between these values, and values are not sorted. So you have to use just linear search. Then how much time is required to search a value in the worst case? For example, if one comparison takes 1 millisecond, for instance, so there are total 2 raised to the power 128 values, and one value means one comparison with one value takes 1 millisecond. So total time will be 2 raised to the power 128 milliseconds. This is not a small number, This is about this much milliseconds. You cannot, I was not able to write this in the same font. And if you convert it into years, these are such many years. So you can just, you will waste your life. But if data was sorted and we are using binary search, it would take only 128 milliseconds. How? It takes log of n time, and n is 2 raised to the power 128. So log of 2 raised to the power 128 to base 2. So according to the rules of log, 128 can become the constant factor of this. So 2 raised to the power, log of 2 to the base 2 is 1. So answer will be 128 milliseconds, and this is just 0.128 second, not even a second. Not even the half of a second, not even the half of a second. It's about half of a second. So can you just compare both these? Maybe my whole race will vanish, but these comparisons will not end. And this is not even a second. And n is same. Now you can imagine how important sorting as a problem is. Sorting as a problem is well studied, and great deal of research has done into devising efficient algorithms for it, because it's not just sorting, it's about efficient sorting. So in this series of lessons, we are going to study, analyze and compare these sorting algorithms, and we have many sorting algorithms like bubble sort, selection sort, insertion heap, predicts, merge, quick. There are many more, distribution sort and counting sort, and much more, shell sort. So this is an open area of research, and we come up with new sorting algorithms. So we will be discussing about some of these sorting algorithms, and we will study what is their algorithm, how it works. We will simulate them, then we will analyze them, what is their space and time complexity, and this is all about it. So when we have so many algorithms for sorting that have been designed over a period of time, so it's better to classify algorithm based on some parameters. So there are many parameters on the basis of which we can classify our algorithm. So one of these parameters is that what is the maximum time taken by these algorithms to sort an unsorted list. Or in other words, we want to classify upon its time complexity. So what is the measure of rate of growth of time taken by an algorithm with respect to input size? So some algorithms will be relatively faster than others, and some will be slower. So sorting algorithm with respect to time can be widely categorized into three categories. First is polynomial time. By polynomial time, I mean quadratic time, cubic time, or something like that. And some of these examples, some of the algorithms that run in polynomial time are bubble sort, selection sort, and insertion sort, and we will study all these inshallah ta'ala. The second one is efficient sorting, and that is n logarithmic time, and we have got many algorithms of this category like quick sort, merge sort, and heap sort. There is another category of sorting algorithms with respect to time complexity, and they are called linear time algorithms, linear sorting or order of n sorting. So examples are counting sort, radix sort, and bucket sort. But what I want to say is that these cannot be used on every type of data. Polynomial time algorithms and logarithmic time algorithm can be used on any type of data, but linear time algorithms can be these are successful when data is limited and in some specific format. So, however, this is another category. Now, the second parameter that we can use for classification is space complexity or memory usage. Some sorting algorithms are in place. In place sorting algorithm means they use constant or logarithmic extra amount of memory to arrange the elements. For example, if there are n elements, so they might require some C means constant memory location or some logarithmic log of n memory locations. But if the number of extra memory location exceed this logarithmic time, then these are known as outplace sorting. It means much of the time is in fact not it means this sorting is not taking place on just the original memory location, on the original array or on the original linked list. It requires much, it requires many other memory locations as well. So it is not in place of the original array or linked list. So we are in fact sorting it out place. So that is why it is called out place. So when some sorting algorithm like merge sort use extra memory to temporary storage of data, and the memory usage grows with input size. So these are called outplace sorting, and here S of n means space complexity is greater than this log of n. You can say constant space. So here it is. So with respect to space complexity, we have got some in-place sorting algorithm like bubble sort, selection sort, insertion sort, and quick sort, and outplace like merge sort and counting sort. So there is a version of merge sort that is in fact in place, but usually it is applied as an outplace sorting algorithm. Now comes the third parameter, that is the stability. Now this is the term that you have to know what is meant by this stability. So by stability we mean that if some values are repeated, if there are duplicate values, so when we are going to sort these, we will not change their relative order. The stable sorting algorithm guarantees that in the case of duplicate values, the relative order of elements is preserved. For example, there is an unsorted list 12, 21, 6, 8 and 6. Now I have colored these just to indicate you, just to tell you what this stable and unstable sorting is. You see this, there are two 6, one with the purple background and one with green. So when we will do stable sorting, it will sort the values in an order 6, 6, 8, 12 and 21. These are all sorted, but you see the relative order between these two 6s is preserved. The one with the purple in the original list was before the one with the green background, and same is the case here. But in an unstable sorting algorithm, when you run that algorithm, so at the end you will get definitely the sorted list, but it is not guaranteed that this 6 with the purple background will always come before the 6 with the green background. So it may happen the other way. So it is called as unstable sorting. So there are two versions of sorting: bubble sort, merge sort and insertion sort are stable, but quick heap and selection sort are unstable sorting. So this is with respect to stability. Now there is another parameter of classification, and that is whether a sort is internal or external sort. And by internal sort we mean that all the sorting, when we are sorting something, sorting will be definitely on RAM, but if we are doing some sorting, whether all the values were loaded into RAM or not. If all the values were loaded in the main memory and then sorting was done, that is called as internal sorting. But if sometimes data is very, very large, we cannot load all the values on the RAM. So then we have to do sorting either in you can say batches, or you can say we have to do sorting on disk. So this is called as external sorting. if the records are on auxiliary storage like disks and tapes, so quite often it is because it is not possible to get all of them in the main memory in one go. So such a sort will call an external sort, and there are some. You can apply any algorithm in an internal fashion or in an external fashion, but mostly bubble sort, quick sort, and insertion sort are used as an internal sorting algorithms, while there is a version of merge sort. In fact, it is a hybrid version. It combines some of the sorting techniques. So this is used as an external sorting algorithm, and there is a algorithm called distribution sort that is very similar to quick sort, that is used as an external sorting algorithm. The next parameter upon which we may classify sorting algorithm is whether algorithm is recursive or non-recursive in nature. Means by design it is recursive or non-recursive, not by implementation. So keep it in mind. Sometime we can we can implement an algorithm written in iterative manner in the form of recursive functions, and the other way around. But I am just talking about their design and their nature, not their implementation. So by their nature, bubble sort, selection sort, and insertion sort are iterative, and merge sort and quick sort are recursive. So you can have, by implementation point of view, you can have a recursive version of bubble sort, but by design it is iterative. So that is what I am trying to teach now. So there is one last parameter upon which we may classify our sorting algorithms, and it is whether algorithm compares the values or does sorting in some other way. So if you are sorting and you are comparing values to see which value is less than, greater than, or equal to, so this type of comparison is called comparison sorting. Is very versatile in nature because it can be applied to any input. But there is another type of sorting technique that is called a non-comparison based sorting algorithm, and it uses the internal character of the values. I mean, it breaks the values in and does operation on those values. So it can be applied to some particular cases, not on the all inputs, and requires particular values. So it is not versatile in nature. So we have got some comparison based sorting, like, but in fact most of the algorithms are comparison based sorting: bubble sort, selection sort, insertion sort. And the one we have learned in the first parameter, that were called linear time algorithms. So about all of them are non-comparison based sorting, because they do not work on all types and all sizes of inputs. So these are like counting sort, radix sort, and bucket sort. So this was all about the introduction to sorting. So I hope it will be helpful. So it might have cleared your some myths and perceptions about the types of sorting algorithms that you have that you had in your mind before listening to this. So if you have got any queries and questions, you may contact me either by email, by phone, or by WhatsApp. I always wait for your queries, but I'm not getting your queries regularly. So I hope things will change as exams are coming now. So this was all for today's lecture.